Hello everyone, welcome back. Today we're tackling a really interesting medium-level problem called unique length-3 palindromic subsequences. This is one of those string problems that seems complex if you try to brute force it, but becomes beautifully simple once you realize there's a fixed structure we can exploit. I'll break down exactly what that structure is, and how we can use it to solve this efficiently. So here's the deal. We are given a string. Let's call it S. Our job is to find the number of unique palindromes of exactly length 3 that are subsequences of this string. Now remember, a subsequence means we can delete characters, but we keep the relative order of the ones that remain. And since we're strictly looking for palindromes of length 3, that simplifies things massively. A palindrome of length 3 always looks like a sandwich, a character, some middle character, and then that same first character again, like ABA or ZZZ. Let's walk through this first example to see the logic in action. We have the string AABCA. We need length 3 palindromes. This means we need a matching pair of outer characters, and something in the middle. Look at the letter A. It appears at the very beginning and at the very end. This is great because it acts as a container. Any character we find between that first A and the last A can form a valid palindrome. In this case, between index 0 and index 4, we have A, B, and C. So AAA, ABA, and ACA are our 3 unique palindromes. We count each unique form only once. Just a quick heads up before we dive in, we'll be walking through the solution using Python, as it reads very clearly. But don't worry if that's not your main language. I'll be showing the full code for Java, C++, and JavaScript towards the end of the video, so stick around for that. This brings us to our first approach, which the editorial calls count letters in between. The intuition here is straightforward. Since a length 3 palindrome is just 2 identical characters surrounding a middle one, why not iterate through every possible character that could be on the outside? For every unique letter in our string, we find its first appearance and its last appearance. The distance between these 2 points is our search zone. Any unique character inside that zone gives us a new palindrome. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first. And don't worry, after that, we'll walk through the most important sections together. Alright, here's the Python code for this approach. It's surprisingly short. We start by identifying all the unique characters available to us using a set. Then, for each of those characters we do the heavy lifting. Let's break down exactly how that loop works. First, letters equals sets gives us our candidates. We only care about characters that actually exist in the string. Then, inside the loop, we use 2 built-in methods. Index finds the first time the letter shows up. Let's call that I. And rindex, or reverse index, finds the last time it shows up. Let's call that J. This defines our range. If I and J are the same, it means the letter only appears once, so it can't form the outer shell of a length 3 palindrome, and our range will logically be empty. Once we have our start point I and endpoint J, we simply look at everything strictly between them. We loop from I plus 1 up to J. We throw every character we find into a new set called between. Because sets only keep unique items, duplicates are automatically handled for us. Finally, the size of this between set tells us exactly how many unique middle characters we found for this specific outer letter. We add that count to our total answer. Now the first approach works well, but repeatedly searching the string with index inside a loop technically costs us some time. We can optimize this with the second approach. Pre-compute first and last indices. Instead of scanning the string over and over, we scan it just once at the start. We'll keep track of where we first see each character and where we last see it. Since we're dealing with lowercase English letters, simple arrays of size 26 will do the trick perfectly. And here is the code for the pre-computation approach. It looks a bit longer, but it's doing the same logical steps, just more manually and efficiently. We set up our arrays, fill them in a single pass, and then process the ranges. Let's verify how we fill those arrays. We create 2 lists, first and last, initialized to -1 to represent not found yet. Then we iterate through the string. For every character, we convert it to a number between 0 and 25, basic ASCII math. If we check our first array and see a -1, it means this is the first time we've encountered this letter, so we save the index I. For the last array, we always update it with the current index I. By the end of the loop, last will naturally hold the position of the final occurrence. The second part of the logic is almost identical to our first approach, but instead of iterating through a set of characters from the string, we just iterate through the numbers 0 to 25. If a character was never found, meaning its first index is still -1, we skip it. Otherwise, we take the indices we stored in first and last, loop through the string strictly between them, and collect the unique characters in our set. Add the size to the answer, and we're done. A quick note on edge cases. What if a character only appears once or not at all? For example, in the string ABC, A starts at index 0 and ends at index 0. Our code tries to loop from index 1 up to 0. In Python, and most languages, a loop where the start is greater than the end simply doesn't run. The set remains empty, we add 0 to our answer, and the code naturally handles it correctly. No special if statements needed. So, how fast are these solutions? Both approaches effectively run in big O of n time. In the second approach, we iterate through the string once to build our arrays, and then we do at most 26 passes over segments of the string. Since 26 is a constant, it simplifies to linear time. For space, we use fixed-size arrays or sets that can only ever hold 26 characters maximum. This means our space complexity is big O of 1, or constant space, because it doesn't grow with the size of the input string. Alright, that covers the main solution in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down line by line, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. You can see we use integer arrays for the indices and a hash set for the characters. Pause here if you want to study it. Next up, here is the C++ version. We use vectors initialized to -1 and an unordered underscore set for efficient counting. Feel free to pause and review. And finally, here is the solution in JavaScript. It follows the same logic, using charcode @ to map letters to array indices. Hopefully, seeing it in your preferred language helps solidify the concepts. So let's wrap it up. The key takeaway here is understanding the structure. Because the length was fixed at 3, we knew exactly what to look for. Matching ends. By finding the widest possible sandwich for each letter using the first and last indices, we maximized our chances of finding unique fillings. And by pre-computing those indices, we made our solution super efficient. Alright, before we go, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now, down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra, but really helps me out. Or, if you're feeling generous, There's always the boba fund. Keep coding, and I'll catch you in the next one.